A pleasant day to everyone. Today, we will discuss our prototype, the process behind its creation, and how we arrive at our final conclusion. First, I would like to introduce our prototype called FLOODAMN, Automated Flood Water Level Detector, Suction, and Multi-Stage Filtration for Sustainable Emergency Water Supply. This prototype activates its suction mechanism once floodwater is detected and reaches the sensor's designated limit. Proceeding with our discussion, we will now present the rationale. Flooding has been one of the major issues in the country. Because of this, the researchers selected an area that is frequently affected by floods, such as Lemery, Batangas. This situation inspired us to develop a prototype that aims to help minimize the impact of flooding on the residents of Lemery through our innovation, in which automation is integrated to provide multiple functions.
As for the statement of the problem, this study addresses the persistent problem of flooding in Lemery, Batangas. Despite existing drainage systems and periodic cleanup programs, many areas still experience frequent and severe flooding, especially during heavy rainfall. One major factor contributing to this is the topography of Lemery, Batangas, which sits on a low lying land that acts like a natural catch basin for rainwater. Its proximity to the Pansipit River further increases its vulnerability as rising water levels and overflow can intensify flooding in surrounding areas. These recurring floods disrupt daily activities such as damage property and threaten health and safety and overall quality of life for its residents. Therefore, the study aims to develop a water filtration system, FLOODAMN, capable of remotely measuring flood levels while also repurposing floodwater for basic household use. In addition to this, it seeks to evaluate the performance of the current preventive measures set. By proposing this, the study hopes to reduce flood risks and support better planning and disaster preparedness within the community.
So now, let's discuss on how our prototype works. Our prototype starts with a water detector placed in a flood-prone area, which is the Lemery. When the water begins to rise, the detector sends a signal or warning to people to alert them about the increasing water level. Once the water reaches a set limit, it enters a tube, and because of a strong water pressure during floods, the water is pushed upward and moves into a filtration unit. The filtration unit has three parts. The first part is basic filtration, where big dirt, leaves, and solid particles are removed. The second stage uses layers of rocks, coarse sand, charcoal, and fine sand to clean the water. As the water flows down, the rock first catch the remaining big dirt. The coarse sand then traps smaller particles. After that, the charcoal removes bad smell, some color, and other impurities. Finally, the fine sand filters out very tiny dirt, making the water clearer before it moves to the coagulation process. The third part is the coagulation process, where a chemical called a coagulant is mixed into the water. The water goes through fast mixing, slow mixing, and settling. In this stage, tiny particles stick together and form larger clumps called flux, which settle at the bottom. After these three steps, the clean water flows into a storage tank. The stored water is not for drinking, but it can be used for cleaning, washing, gardening, and other personal uses. This system helps reduce floodwater and turns it into something useful through simple detection and multi-stage filtration. And now, let's proceed to our next slide, wherein it showcases the features of our prototype, which are the water level detector, water filtration system, and the water suction. Also, in our presentation, you can notice the internal wirings of our water section. It also showcases the front view, top view, and the right side view.
Floods remain one of the most dangerous natural disasters, causing significant loss of life and property worldwide. Many communities are unprepared, and early warning systems are often limited or absent, leaving residents highly vulnerable to flood risk. Traditional flood monitoring methods such as manual water level measurements or CCTV observations are slow, prone to human error, and cannot provide real-time information, which increases the risk to both people and property. To address these challenges, automated water level monitoring systems have been developed. Mohammed et al. 2019 designed a system using ultrasonic sensors, microcontrollers, and IoT technology to provide real-time water level updates through mobile applications. In the Philippines, where floods are frequent due to typhoons, similar systems have been implemented, such as Mandulog River systems, which sends SMS alerts and predicts potential overflow times to enhance preparedness. Since floodwaters often contain debris that can clog suction systems, filtrations become an important part of flood management. Multi-stage filtration has proven effective, combining screening to remove large debris, layered filtration using rocks, coarse and fine sand, activated charcoal and cloth, and finally coagulation to remove finer particles. Activated charcoal has been recommended as an inexpensive and effective filter material, and coagulation improves filtration performing depending on the coagulant used. Overall, combining automated flood monitoring with multi-stage filtration provides communities with timely alerts and cleaner water, reducing risk to life and property and offering a cost-effective solutions for flood-prone areas.
Here, we present the timeline and progress of our project, including the planning phase, immersion activities, outputs, and final submissions. From October 26 to 28, our team focused on formulating the main topic, conducting comprehensive brainstorming sessions, and identifying the specific location that would serve as the core focus of our study. During this phase, we ensured that our topic was relevant, feasible, and aligned with the needs of the community. On November 2, we worked on preparing a draft of the key questions for our interview and data gathering activities. We also began identifying possible solutions to the problem we intended to address, forming the foundation for our immersion. On November 15, our team conducted the community immersion and interview. We gathered essential information, observed real-life conditions, and listened to the concerns and insights of the individuals involved. This stage provided us with meaningful data that guided the development of our outputs. On November 16, we started drafting the narrative report, which included the documentation of our immersion, interview results, observations, and initial analysis of the problem. By November 26, all assigned outputs were required to be submitted. This included immersion documentation, simulation, infographics, compilation of all audio recordings, PowerPoint presentation, video version of the PowerPoint presentation. Each member submitted their designated part to complete the overall project requirements. On November 28, we submitted all final outputs including the completed PowerPoint presentation, prototype simulation, community immersion outputs, required forms, infographics, and all video recordings. This marked the completion of our project requirements. In summary, our project progressed through systematic planning, active community engagement, and comprehensive documentation.
The project will significantly benefit residents, motorists, and vendors by mitigating the impacts of flooding, which cause traffic delays and affects livelihoods. Farmers could use the filtered water for irrigation, improving crop yields. Residents could also utilize the filtered water for household chores, such as cleanings and watering plants, addressing water scarcity during and after typhoons. By reducing flood waters and providing recycled water. This enhances daily life, minimizes disruptions, and supports agricultural activities. Ultimately, it contributes to a more resilient and sustainable community.